Aerospace and Mechanical Engineering Lab 2. Today we are going to continue our discussion on numerical modeling, and we will discuss Lab 7, which is essentially going to be the lab that you will have to do after a spring break. The Lab 7 is going to be very similar in the setup and how you actually should do it, and the lab reports is going to be very similar to Lab 6 and Lab 8 after it, which essentially means that you have to do the lab and upload your screenshot or the file itself on Blackboard as a lab report. And these won't be graded. We just want to make sure that you actually do this during the lab time or do something during the lab time. And then eventually all of the results from Lab 6, Lab 7, and Lab 8 should be lumped together and submitted as one single lab report / mini project. And so be on the lookout for the lab instructions for Lab 8. And let me know if you have any questions. Let me know, your TA know if you have any questions. Today we are going to talk about CFD, or computational fluid dynamics. And the software of choice here is called Fluent. If you come to these analysis systems, you're going to see that there is a fluid flow option that says Fluent. We can also choose the Fluent. We should be able to choose it from the component systems, but we don't really need to do that here. We can just use the analysis system right here. So drag and drop. You want to drop it on the mesh that you have created. It will take a little bit of time to import the geometry and the mesh. And you don't really see a check mark beside the mesh. This is how Fluent operates for some reason. You have to make sure you click on the mesh and right click and update the mesh. We don't really get the update component here, so we have to go back here, right click here, and then click update. This update will be imported to Fluent module automatically. You have to give it a little bit of time for the mesh to update. You have to keep in mind that this is a three-dimensional mesh, and in general, it will take longer for our software to simulate this, because it's three-dimensional mesh and we have a lot more cells compared to a two-dimensional geometry. Okay. Yeah, so you see the check mark means that the mesh is created and successfully imported to Fluent. Then the next step is to open the setup tab, which will open the Fluent software for us. If it's the first time you're opening this, it will ask you to allow things. If it's a lab computer, you should click cancel. If it's your personal computer, you can allow like connection to internet and whatnot. So you get a couple of options here. We are solving a three-dimensional case, so this is grayed out and it's chosen for us. The solver options calls for double precision. The options we have here is double precision, which essentially makes the precision of your simulation a little more. And this is computer precision. This is not our simulation precision. So essentially, well, it means that instead of going to 16 decimal points, 16 digits after the decimal point, it goes to 32 digits after the decimal point. That is not something that we need to select. That doesn't really increase the accuracy of our simulation for this specific lab. But in general, if you check this, it should increase the accuracy marginally. And then the other option is we can tell the software that we don't want to see these options anymore. The last one is the number of processes we can use. If you have the full license, you can select as many processes as your computer has. If you don't have the full software, if you're using the student version like I am, the maximum is 4. The maximum number of processors you can use is 4. You definitely want to increase this because it will speed up your simulations. There are a couple of other options. We can change the root path. We can display the mesh after the reading. We can load a CD start page. Don't really need to check that. It is asking us about the parallel settings. It is asking us if we want to use remote Linux nodes, which none of these do apply to us. We can have a scheduler to run. Since we are not using the remote Linux nodes, we are not using the scheduler. The scheduler is a different animal by itself. And we can also change the environment variables. None of these need to be changed. So the only thing that I changed here is the solver processes. You can also check the double precision if you want to, but it is not necessary. Next step is to click Start. This will also take a little bit of time to start. Again, you cannot allow this on allow any of these things on lab computers because you don't have admin access. You just have to click cancel for all of them. But on your personal computer, you can allow them, and like allowing them or canceling them, not allowing the connection to internet is not going to change anything as far as the simulation goes. But it just means that ANSYS will receive diagnosis data for most cases. So we are still waiting for things to load. I like the dark modes in general, so I want to apply a dark mode theme. You do not need to. Okay. So our CAD geometry is imported. We can see we can see the cutout here for the traffic light, and we can see the inlet and all of the outlets we have set up. I'm using the middle mouse button to rotate this. You can do the same as well, and we can actually realign the whole thing. There are a lot of options here. As you can see on top, we have the file tab, which is you can read and write, you can save your project, you can do a lot of things with the file tab. But the only thing we really need to do here is saving or importing our project. The next part is domain. This will help you change the mesh if you need to. And we don't really need to change the mesh here. We can also set the units if we need to change the unit system. And for acceleration, everything is set in SI here. But if you do want to use the imperial system, you are welcome to. You can just come here and change all of these units. The conversions will happen automatically. We can check the mesh. We can check the quality of the mesh. And there are a lot of other options. We can scale the mesh. We can transform the mesh. We can change the zones. And we can create interfaces. We can also change the mesh to a dynamic mesh. Dynamic mesh essentially means that it does change your mesh based on your solution. We don't really need to know any of these things. The next option that's given to us is the physics. We can change the solvers, we can change the materials, we can create and remove zones again, the physics zones specifically, and we can a strength of Fluent is this part, actually user defined. You can actually write a code that is based on C language and create your own solver within the Fluent environment. Again, this is too advanced for us, so we are not going to talk about these. The next tab is the solution tab. We can change the methods. We're going to see all of these later on. And then the post-processing or dealing with the results. And we can also change the views. The rest of these, we don't really need to know the rest of these tabs. But the exact same setup is given to you in this the left panel right here. I usually use this panel because I'm used to it, but you can also use the top panel for most of the things that you want to do. So for the setup, we have the general setup options, and this the task page, whenever you double click on a setup, it will change the task page. So the task page is specifically talking about the module you have selected in the left panel. So we can scale the mesh, again, exactly the same options we had on top here. We can change the solver to pressure-based, density-based. This talks about whether your flow is incompressible or compressible. We are dealing with incompressible flow for most cases, so we don't really need to change this. Velocity formulation, this talks about your frame of reference. You want to have an absolute frame of reference or relative. You want to keep this to relative. In the interest of making things easier, we are going to deal with a steady state simulation. So nothing is changing with respect to time. Since we are dealing with air, we do not need to simulate gravity. But if we were dealing with water or any other heavier types of flow, you want to check this. I will ask you what the direction of gravitational force is. So next step is to go to models. Models essentially is asking us to determine the type of physics we want to have. Do we have a multi-phase model? And multi-phase model is essentially talking about a gas and liquid combined, or two different types of liquid combined. Like think of a boiling scenario where you have water vapor bubbles within a pool of liquid, which is, again, this is not something we want to simulate. Next part is asking us whether we want to turn on the energy equations. We want to solve the energy equation to have an understanding of the temperature field here. Since there is no heating involved, we don't need to solve for energy. We don't need a temperature map. The next part is something that we are interested in. This is asking us whether we want to include the viscosity effects in our simulation or not. Essentially, we can neglect the effect of viscosity and run an inverted model, or we can include the effects of viscosity, run a laminar model. This is a low speed, very low speed viscous model, or we can choose any of these turbulent models. And we need to choose one of these turbulent models. Doesn't really matter to me which one you choose. You don't really need to know what these turbulent models are, but we usually choose this one, K omega, which is all around a good model that can serve us well. Okay. Again, this is not a physics or turbulence modeling course, so I don't really expect you to know any of these, but you can just look them up online and learn if you have to. All of the other physics that are included here is not of our concern, but you can see you can model the electromagnetic fields using the battery model. You can model like a species combustion, for example, if you want to. You can model a heat transfer in a heat exchanger. You can include radiation in your model if you want to. But again, for our simulation, which is the introductory simulation, we are only going to focus on the viscous effects. Next step is the materials. We have two different types of material, a solid and a fluid. Our fluid is said to be air, and the solid, which is the aluminum, which is the traffic light beam, is said to be aluminum. You can change this if you want to. You can change both of them. Just have to click on them and go to create or edit. You can change the material here from their database. But I'm going to keep this as is. Okay. Cell zones conditions talks about the domains we have. We have only one domain in the CFD, which is the fluid domain. Okay. And the fluid domain, it is named solid for some reason, but if you click edit, you see that the material name is air. So we can change this to fluid, but we don't have to because the material is already set to fluid. All of these other options do not exist in our simulation, but you can essentially have a 3D fan zone if you want to. Let's say you are simulating a mulcher, a garden leaf mulcher, essentially, that you use in a garden. As some part of it, you need to include a three-dimensional fan, right? Without actually designing a CAD model for the fan. There are a lot of other things that you can actually do with your model. So I just change the name to fluid. And then the next part is boundary conditions. So boundary conditions are essentially talking about the conditions at your boundaries. Since we're dealing with a three-dimensional simulation, our boundaries are these surfaces. And we have already named them. We have already named them in the previous lab. Like we have an inlet, we have a wall, and we have a couple of outlets. We can change all of these names. We can actually change all of the boundaries if you want to, but we don't need to change any of them. We just have to send the conditions. So for example, if we are setting an inlet boundary condition, we have to assign a velocity or pressure to this inlet boundary condition. So what you do is you double click on the boundary conditions. It will bring all of the boundaries for you. So we have an inlet, gives you a lot of options here. You can change the type. This is already predetermined to be velocity inlet because we named this inlet in the previous step. But we can change this if we want to. There are a lot of other options we can use. I'm going to keep it at velocity inlet and just edit the velocity. So airflow coming in. Again, a lot of options. We have momentum tab, thermal, radiation, species, all of these other ones that are grayed out for us because we are not solving for temperature or radiation or combustion or we don't have a multi-phase flow. And then the velocity specification method, which velocity is a vector. So we have to tell the software how to deal with this vector. The default option says magnitude normal to the boundary, which is fine for our simulation here. Other options is magnitude and direction. So essentially, if you want the air to come at your beam at a different angle, you can just set it here by setting the magnitude and the direction of the velocity. And you can also define it by its component of velocity, x component, y component, z component of velocity. Again, the same thing as magnitude and direction. But we want this to be normal to the boundary for this specific simulation. The reference frame is absolute, which is something that we had already set. We don't really need to change this. And then here, we can just set the velocity. I'm going to set it to 10 meters per second. This just to run this simulation. What you need to do is you need to run this at different velocities. And I would say it's not a bad idea for you to actually find out what a typical wind gust is, or what a wind gust is during a storm, and then set those velocities here. We are not dealing with supersonic or initial gauge pressure. This can be set to 0, and this part of it is related to turbulence. We don't really know the physics at this point of turbulence, and I don't really expect you to know this. So you can just leave this as is and hit apply and close. So yeah, set the velocity to 10 meters per second. The interior part it says interior solid, but again, I think this is referring to the interior liquid, just a naming. Probably in the previous geometry building or the meshing thing, we forgot to change the physics to fluid, computational fluid dynamics, but this is just a naming problem. We don't really need to worry about this, but we can check the interior. Again, it's just a name. We can change the name if we want to. Then there's an outlet at the back, which is this outlet specifically. It says pressure outlet. We don't really need to change the options for a pressure outlet at all, at least for this simulation. Just want to make sure that the backflow direction, all of these are going to be set by default. You just have to use the default values. But there are other outlets outlets that you can use, you can actually set this to a velocity inlet as well, which is the thing we are going to do for the other outlet boundaries. Why do we do this? Because it is going to be easier for the solver to handle if you set a predefined velocity for your outlet. For the main outlet, which is the outlet which is essentially exactly in front of the inlet, we should not define a specific velocity. We should let the solver decide what the velocity is going to be. But for the other outlets, which are not going to be our main outlets, these three, we can just define a velocity and make things easier for ourselves. So outlet left, I'm going to change this to velocity inlet. And you're going to see that this actually changes to inlet. This time though, we can't just set it normal to the boundary because it has to be in the same direction as our original flow. Okay, so I'm just gonna say I'm gonna define the components. To define the components correctly, we need to see what is the direction of the main flow. It is in the positive y direction. So all of the other components has to be 0. And in the positive y components, we're going to get 10 meters per second and hit apply. Same thing for the other outlets, except for the outlet back, the main outlets. Okay, again, components, it has to be positive y direction. So if you change the velocity, you have to come and change all of these velocities. Just have to keep that in mind. Okay, change this to components again, and in the positive y direction. Why is it in the y direction or the x direction? It goes back to the geometry. It doesn't really matter, right? So there's nothing to worry about here. And then we have the wall boundary, which is acting as the ground, the asphalt, whatever, like the ground that you have. It gives us a lot of different options. We can have a moving wall, we can have a stationary wall, we can define the viscous conditions and also the turbulence conditions if we want to, but these can be left as default because we don't really have a moving wall. No slip conditions, which means that 0 velocity at the wall is fine for us. So I'm just going to hit apply and done with it. And then we had another wall. I'm not really sure which wall this is. So what we are going to do is that I'm going to hit display mesh and then deselect all of these other walls. Let's see what this other wall is. Okay, this is our main wall. So what is the wall solid then? Okay, so this is this wall solid. Let me actually is a part of our traffic lights. I think I might have messed this up. So let's see. This just is this is what happened. I'm sorry for the confusion, but when I was naming the boundaries in the meshing step, I forgot to select the ends of the traffic light. That's why it was automatically chosen to be a wall solid. That doesn't really matter. I mean, it is a wall for us anyways. And I'm glad that the Fluent actually caught this mistake. So we are analyzing air right now that is coming in this direction towards our traffic light. So all of the boundary conditions we needed to set are already set. And then the other options are just mesh modification options, we do not need to change anything for these options because we are not dealing with dynamic mesh. The last part is the solution part. This is essentially the mathematical method that the Fluent software is going to use to discretize your partial differential equations that govern the fluid flow. Do we need to know what the mathematical methods are? No, you don't need to know for the purposes of this lab, but it's not a bad idea to Google them and learn more about them. So, as far as you are concerned, this scheme, the pressure velocity coupling scheme, does not need to change. Okay, the same thing is true for this spatial discretizations. But as a general rule of thumb, you can see this order, the second order. We have first order for momentum, second order. Second orders are in general more accurate, but less stable. Meaning that if you run them, you should use second order and higher, like third order. You should, in theory, get better results because you're using a better discretization scheme. But using this might introduce some instabilities to your system that will result in the solver diverging, meaning that the solver giving you garbage results or breaking completely. Okay, so you just have to be careful when selecting this. But as a general rule of thumb, changing this to third order should increase our computational expense, first of all, but second of all, our accuracy. I'm going to leave all of these to second order upwind, which should be fine for our simulation. Next part is the relaxation factor, which essentially means that we are relaxing our next iteration's values. Let's say you solve your domain once, you get a value for pressure, and then you have to use that value for pressure as the initial value for the next time, next iteration, next pseudo time. And what this does is it multiplies all of your pressure calculations or the pressure difference between the two time steps by half, which essentially means that we are marching slower in time. This will increase the stability of your solver. You don't really need to change anything here. As long as you understand what these are, you should be fine. And then here the report definitions are essentially the forces or the flow rates or whatever that you want the solver to calculate for you. The solver automatically gives you the velocity field, the pressure field, whatever you need, the heat maps, but it doesn't really give you values for force that is exerted on the traffic light. To calculate that, you have to come here and create a new report definition. It gives you surface reports, like force on a traffic light is a surface report for us, so we should be able to see force here as well. It gives you volume reports, like total mass flow rates, total mass that is in a system. We have a force report separately, drag, lift, moment, and a specific force that you are interested in. You can actually define this here. We have flux reports, mesh reports, and all of these. You can also define a report definition yourself. We are not doing any of these here, so we can just leave it be. And the last one that we want to discuss in the solution or in the earlier part of the solutions is the monitors. These monitors, you can monitor your report file, you can monitor your report plots, which is essentially the files and plots that are going to be shown to you while the simulation is solving. But the parts that are of our interest is the residual part. The residual talks about the error, the acceptable error in the simulations, right? For all of them, by default, it is set at 2.001, 1 in -3. You can make this more accurate. You can go up to 10 to the -10, 10 to the -12, 10 to the -16. But for the purposes of this project, 10 to the -3 or 0.001 is a good error in our system is an acceptable. So what happens is our solver solves the domain, solves the problem in all of the cells, and then does it for all of the domain once, and calculates new values for pressure, velocity, and all of those, and compare it to the initial values or guess values that we have assigned. If the difference between these two, a final solution of an iteration and initial solution of an iteration, is less than 0.001 for all of the parameters, then it will spit out a solution. It will tell us that we have reached a solution. We have converged to a solution. Okay, so, and we are going to see the evolution of these errors when we solve this for all of these parameters of interest. Okay, so the last part before actually running the simulation is the initialization. Again, the way we solve these problems is we start with an initial value, we solve the domain once using those initial values, and then we spit out another final value for the iterations. This final value for iteration 1 is going to be used as the initial value for iteration 2, and so on and so forth, right? And then the comparison gives us the error and whatnot. So we need to do an first time initialization. This is your first guess. This first guess can be very far off, or it can be very close to the actual results. It does matter if your first guess is very far off. It will take your solver longer to converge to a solution. Think of the Euler methods to find the slope of a curve in your numerical methods, which is essentially very similar to that. We have two different types of initialization, a standard or hybrid. Hybrid does the initialization for you based on your physics. So it is better to use the hybrid. It's better and easier. Like this other one asks you to guess the initial values for all of the parameters yourself. We're going to hit initialize, and you can see that it does the initialization 10 times for us, and eventually reach the tolerance or error value of 2.6. Their goal is to reach at 1.6 for our initial values, but that they haven't reached that. Doesn't matter. We don't really need to be concerned about this. And eventually we want to get to the calculation activities. Run calculation. We don't really need to do the calculation activities for the purposes of this project. So we have a pseudo time step setting. This is just to help the solver reach a better solution. You don't really need to do anything for this. You can actually turn it off if you want to from the solution controls, solution methods right here. You can turn off the pseudo time stepping off or global time step. But since it does help with the simulation, we don't need to turn this off. And then you have to set the number of iterations that you want your solver to go. The number of iterations that you set, it is not the same as reaching the solution. So if your solution is not converged to a final, to those desired error values, but you hit the limit of the number of iterations, the solution will stop, the simulation will stop, but you don't have your final solution. You might be able to accept your solution, but the error values are going to be larger than 10 to the negative 3. So if this happens, if you hit the final iteration value, but you have not reached a final solution yet, you want to make sure that you actually run the simulation again. And it's very simple. You just have to come here and hit calculate again without making any changes. For the time being, we're going to start with 1000 iterations, and then we are ready to hit calculate. Okay, so you can see we have the residuals for all of the parameters. Again, these residuals are the errors, the comparison between the final solution and initial solution during iteration for each iteration. For iteration number 10, 11, whatever, you can see the error for omega, which is a turbulence parameter, is dropping rapidly, it tells us we don't really have that much turbulence here to begin with. The y velocity and the z velocity errors and also the x velocity error have already reached the desired value for errors. The only thing that is still working on is the mass conservation or continuity, right? And if this reaches 1 to the -3, then we have reached our desired simulation results. It should take more than 60 iterations to reach a solution in general. In your report, you want to make sure that you actually are using a finer mesh if it's possible, meaning that the number of cells that you want to make sure it is higher. But we are not solving anything complicated. So for the purposes of this project, 90, 100, or 200 iterations should be more than enough. Let's check the continuity errors again. It is 4 times 10 to the -2. It is going up. As you can see right here, you can see that it is going up a little bit, meaning that one of the simulations actually resulted in worse results compared to initial guesses. But our solver can handle this. There is not an issue for the solver, hopefully. But one thing might happen in your simulation. You might see these residual values go up instead of going down. Go up with a very sharp gradient, with a high gradient. That situation is called divergence, meaning that your results are diverging from each other. Your final result is very, very different from your initial results. And that is when your simulation breaks, your simulation diverges. You need to go back and change things. You probably have said something incorrectly. You need to go back and change things to get the desired solutions. I did expect this to, reach a solution sooner. I tried to make things as simple as possible. Well, let's just wait for it a little bit. I'm going to pause the video and come back whenever we have reached the solution. Okay, we are done with the simulation, and now is the time to actually see the results. You can see the results from here, the results section on the left panel, or you can close this and go back to Workbench and look at the solution results through the post-processing the Workbench offers. You don't need to. You can just use the whatever you want to do here. Okay, let's go to the contours. We want to see contours or heat maps of pressure. I'm going to double click here. It says contours of pressure, static pressure, and then a lot of other options for the contours. But we don't really know where to look at for the contours. Looking at the contours of inlets and the outlets is not very useful for us. The surface of the traffic light itself is also not very useful for us. So what should we do? We have to create a new surface. Essentially, I'm going to cut a surface in the middle of my mesh right here. So cut a surface in the y direction. I think we might have set the velocities wrong. Let me actually go back and fix the velocities. I'll come back. Okay, so I had make a little bit of mistake in setting the velocities at the outlet bodies. If you recall, we did set velocity at the side and the top outlet bodies. I said the velocity is actually goes in the y direction. It is incorrect. Actually, flow has to move in the x direction. Okay, so let's go back. Let me delete this contour. Let's go back to our contours. We want to create a new surface that cuts through the middle. So the new surface has to be in the x direction, right? And has to cut through, has to be in the middle of the y-axis, somewhere here. So, and we want to create a plane. This plane has to be, it is asking us what type of plane do you want to see. We of course don't want to see a YZ plane because we are interested in knowing what happens to the flow around the traffic light. So this has to be an XZ plane in the middle, exactly. And it is, they are the default to the middle of the surface. So what we are going to see is the flow around this beam. I'm going to hit create. It is named plane 8, and I'm going to show the pressure around plane 8. This is my pressure distribution, as you can see. We can also see the velocity around this beam. By looking at the velocity, I can tell that our simulation has not given us correct results. So we need to make a couple of changes, see what happens. Or we have not reached the final solution yet. And this is definitely the case because I wanted to showcase, I wanted to fix the flows and come back to this, fix the velocities and come back to this, and see what happens, show you how to actually do the post-processing. But we can see the contours like this. If you need to see the streamlines or the velocity vector, you can just define a new vector on the same plane. So it gives us all of the velocity vectors. The velocity vectors around our beam are fine, are acceptable solution. But in the middle, for whatever reason, we have an increase in the velocity, which is not acceptable. We can also look at the path lines. The path lines, again, on the same plane, tells us how the flow is moving around the cylinder. I think there is an issue with the boundary conditions that I will fix and come back to give you final results. But this is what you need to do for the computational fluid dynamics part of the class. You need to run the simulation, you need to get correct results, and then take the screenshot of your heat map of velocity, heat map of pressure for like 2 or 3 different velocities, and put it in the final lab report that you're going to submit after lab 8. You have to keep in mind that that final lab report is worth 15 points, not 5 points. So this is definitely worth more. You can treat it as a mini project, if you will. Okay, I went back and checked the simulation. I think my naming was incorrect. This is a three-dimensional thing, so it is a bit more difficult to visualize. And these things happen while you're doing the simulation. So you just have to be patient with your model, with your simulation. I have set the inlet to be in the actual inlet, which is essentially bringing air in the Y direction. So what I'm going to do is I'm going to use one of the outlets, the correct outlet, essentially this boundary as the inlet. Let's see which one it is. Yes, so all of the outlet back is also outlet left. So outlet left should be our correct inlet, and outlet right, I assume, is going to be our correct outlet. I'm going to make these changes and show you final results. Okay, so we are back finally. This is what we wanted to get. This is our magnitude of velocity field. This is our wall. This is a cross section of our beam. We can also show the beam itself in our contour to a three-dimensional beam. Let me actually select all of these. You can see the velocity at the walls is zero. velocity is the highest on top and the bottom of the beam and lowest in front and the back of it, which is a desired result. Again, that my boundary conditions were incorrect, so I had to fix the boundary condition. You can see the pressure distribution here. Again, lowest pressure on top and the bottom, and the highest in front and back of the beam. This is what we wanted. Eventually, we want to import this pressure data into a static structural module and do a deformation analysis. But you want to make sure that you set everything correctly, and you want to double check and triple check everything before actually running. A debugging process or troubleshooting is a part of the simulation, so don't be discouraged if you make a mistake. The mistakes happen. As you can, there's a lot of different things that go into these simulations, and let me know if you have any questions. Enjoy the rest of your day.